start this recording. Good morning. All right. It's Thursday already. I can't believe it. And we're almost done with February. Thanks. I mean, it's a good thing. It's kind of a good morning. Kind of a flyover month anyways. So, quick review. We talked about exponents and logs. There was a lot of stuff going on in there, but just in general, right? We talked mostly about exponents, exponent laws, right? And we went through them all and we talked about them all and then we used them. And so obviously we can't go back and redo last day, although it was fun, right? So can go back and review those. And then we introduced logs, right, or logarithms, okay, as a way of solving for x when it's in the exponent, right? So, and exponent laws, we also including roots, right? Roots or radicals, we can call them. So including roots, where we just raise it to the power of 1 over n for the nth root. Okay? So that was just last day, so I'm not too concerned about reviewing it. It's going to come back up today, so not to worry. So we introduced logs as the method for solving for x when it is in the exponent, Okay? We didn't do anything with that yet because we need some log laws, but we introduced the idea at least. Okay? So if we have something like, so for example, if you have 7 to the power of x, right, and you want to solve for x, we need logs. To solve for x, we need logs. Okay. So as a reminder, there are, depending on how much math you've taken, you probably know that there are logs of different bases. We're going to work exclusively in the natural logarithm, so ln. Okay, log base e. That doesn't matter to us. There's an ln button on our calculator, so we'll just use that as our log. All the logs behave the same, so all the log laws that were I know, fun to say, fun to do. All the log laws that we're going to develop here apply to all the bases, but we're just going to use the natural log. Okay? So remember in this course, we will use the natural logarithm. So we will use the natural log, ln. And I usually do a little script ln, right? And I think I mentioned it last day. It's because I have spent years and years and years working with ln, and so it just becomes this kind of script ln. So ln or ln, I don't know how else to write it. Okay. So in this course, we'll use the natural log exclusively, but all the log laws apply to any base, apply to logs of any base. That comment actually assumes that you know a little bit about logs. So anyways, I don't really assume that you know anything about logs, hopefully a little you've seen them or worked with them before, but you might not have gotten to the log laws. So here we go. Let's just jump right into it. We will talk about these log laws and then we'll use them in some examples. Okay? But we'll use them later on in the course as well, right? So let's just kind of sneak peek. And if you look at your formula sheet, where's the formula sheet here? Right? In chapter 5, that's the first time where we see an exponent here. And what if I need to solve for n? Well, then I need some method of solving for n, right? So I need some way of isolating n and bringing it downstairs. And you can see here, it's already worked out for you in this case, right? But we're using logs. So we need to know where those came from. And so that's why we're talking about it today. Same thing here. We've got multiple powers here. We've got a power of e to the r times t. So we need to be able to solve for r and t, right? So we need methods to be able to do that. So that's why we need this, right? So log laws, here we go. Properties / rules of logs. Math is just a game, but we need to know the rules, right? So I call them log laws, or Bob Loblaw's Loblog from Arrested Development. Thanks. First, we're going to establish that A and B are going to be positive numbers. So we denote that by A and B are in the set of the set of real numbers, but positive real numbers. I'm just going to clarify this. This is just saying that A and B must be positive. Okay, that's all that's saying. So don't be thrown off by that notation. I know we haven't spent a ton of time on that notation, so don't worry about it, but it just says A and B must be positive in the following rules. Rule number 1. And rule number 1 is the one that we use kind of the most, okay? And so that is, if I wrap a log, now here's where things might get confusing, right? Like I said, ln is the only log that I use, right? In statistics, in math, in all my fields that I work in, we just use ln. So a bad habit that I have developed, and I'm not the only one, but is I just call this log. And I know that's confusing when you're first starting, but because we've established that we're only going to use ln as our log, right? We can just call it log, right? So here, I'll just clarify, I read ln as log, right? So whenever I see an ln, I just read it as log. And I know that's confusing to a lot of people when you're first starting. Then you get into the groove and then it's fine. And oh, okay, when she says log, I think ln, right? So the log of a to the power of b, notice that I've wrapped a log around a to the power of b. So, and what we said is, okay, we need these logs to be able to solve for the exponent. Well, here's how we bring it downstairs. It's by this first property that says I can rewrite this as b times the log of a, right? So by this property, this is how I'm going to be able to bring something kind of downstairs, right? So that's how I use logs to bring things down from the exponent. So I'll even use a more dramatic color here, right? This is how we will be able to solve for b. Okay. So that's our kind of number one rule. Second rule, very similar, and I mean, you might argue that they're the same, right? The natural log of a to the negative b, well, what do you think it is? Just looking at the first rule, well, yeah, it becomes negative b times the natural log of a. One thing that I want you to remember, though, is that a to the negative b from last day, that's the same as 1 over a to the power of b, right? So you might have to rewrite it as an exponent, right? If you have a fraction, you might have to rewrite it as an exponent before you can take the log, right? And so here, recall a to the negative b is the same as 1 over a to the power of b, right? So sometimes you might have to rewrite it as an exponent before you can keep going. Okay. The third law. Third law is kind of interesting, is that if you have the natural log of a, and I'm trying so hard to call it the natural log, but let's just call it the log, save me some time. The log of a plus the log of, plus the log of b. Notice that we had logs of the same base here. If I'm adding logs of the same base, if I want to simplify that into one log, what happens is we end up multiplying a and b, okay? So here, this becomes the log of a times b, right? So what we're saying here is to simplify, I'll just say logs of the same base being added together, we multiply inside the combined log. That's pretty interesting, right? And so the fourth and final rule, not 10 rules like for exponents, right? So there's only 4 laws that we need to have a really good handle on. But if I want to simplify 2 logs of the same base being subtracted, right? And you can kind of get there by figuring out what subtraction is, right? But so let's just hold up. But then it becomes division inside. So let's just write it out and see what happens. So the fourth law is that if you have the log of a minus the log of b, it actually becomes the log of a over b. Let's convince ourselves here what's going on. Well, subtraction is just really multiplying by a -1, right? So adding and then multiplying by a -1. This here, this negative, I can bring back upstairs by that law number 1, right? Or, I mean, in theory, by law number 2. We don't really need law number 2, but, right? And so here, notice that the log of a minus the log of b is the same as the log of a plus -1 times the log of b. And this isn't something that I'm going to test you on or anything like that. I just want you to see where things are coming from, and it's not as bad as it looks. So here, this becomes the log of a plus the log of b to the power of -1. All right, I can by log rule 1 or 2, they're the same. I can bring this -1 upstairs. right? And so really now I have a and 1 over b here, but they're being added. So this becomes the natural log of, a times b to the negative 1, which is the same as the log of a over b, right, by those exponent laws. So they all go hand in hand and they're all related. Okay. So those are the log laws, and you'll need to have them handy, right? And but you can see how they all kind of fit together. They all use each other. So now let's try using these log laws to solve some problems. Did I start with, no, not yet. Okay, so just a quick example.
Emily, are you able
Yes.
just to can you write an explanation just like you did with 3?
Yes.
Thank you.
It would be the same, but if they're being subtracted, then you divide.
Perfect.
So, to simplify logs of the same base being subtracted, try to squeeze it in here, we divide inside the, so subtracted, we divide inside the combined log. Okay, I did it. Okay, so now let's use these log laws. If I tell you that 4 is equal to 3 to the power of x, and I ask you to solve for x, if we didn't have logs, we'd be stuck, right? So, but now remembering that, okay, if I have something in the power, oh, sorry, it's lagging, something in the power that I want to bring down and I want to solve for the exponent, right, then I can use this first law, right, that says, well, I can actually rewrite something like this as this, and it's equivalent, right, because we've got this equal sign. So to get there, what I have to do is I have to take the log of both sides of my equation, and then I can apply this property, right? So to bring this, to bring x, I call it down or downstairs. I know that's weird, but to bring x down, we need to take the log of both sides. Right, whatever I do to one side, I have to do to the other side. So I'll start and just write out the original equation, 4 equals 3 to the power of x. So then my next step here is going to be to take the log of both sides. So here, this becomes the log of 4, and you don't want to forget to take the log of 4, right, is going to be the log of 3 to the power of x. If you wanted to, you could even skip, but here, this is our first example, so I'm not going to jump right to it. But in the future, when I take the log, I'm actually going to bring that x down immediately. So I'm actually going to skip to this step, x times the log of 3. So the log of 4 is equal to x times the log of 3. So usually I'll just skip straight from here, the first step, to this third step, because that is why I'm taking the log, right? So you don't need to show this step, but I want to show it because it's our first example. right? So here I'm moving from this line to this third, so the second line to the third line by law number 1. By law? No, by law number 1. Rule number 1, or whatever you want to call it. Okay. So now I've just got, and remember, right, if you try on your calculator and you take the ln of 4, right, I specify ln because you've got a log button and an ln button, so you want to use the ln button. If you take the log of 4 and then the log of 3, those are just numbers, right? So here, these are what we call the exact values, log of 4, log of 3, these are our exact values, and then we'll get a decimal approximation, right? But to do, to find, for example, the log of 4 on your calculator, it works a little bit differently than most calculators. So you have to have the 4 on the screen first, and then you hit the ln, and then I think you have to hit equals. We'll do it together, but before we do that, I'll finish this. I'm so close though, right? So here, x is just multiplying the log of 3. So if I have to solve for x, I will be doing a little switcheroo, right? I like to have what I'm solving for on the left-hand side, but then I'm also dividing both sides by the log of 3, right? So here, this is where, at least when we first do it, people get confused, but then if you take a step back and see what I did, right? So here, I like to have the, well, first I have to divide both sides by the log of 3, right? So I have to bring that log of 3 over here, but then I don't want to have x on the right-hand side. I like to have it on the left-hand side, so then I do a little switcheroo, okay? So this is what we would call the exact answer. Right? There's no decimals here. This is the exact answer. Because I've got numbers in here, this is just going to be a number, right? But to find the decimal approximation, right, we need to use our calculator. So to find the decimal approximation, for x, we need to use our calculator. Okay. So to take the ln of 4, we have to first have 4 on the screen and then hit the ln button. So here, do 4ln to find the log of 4. So I'm going to go to our calculator. I'll just use the one I have here. So again, I have to have the 4 on the screen. And then I hit the ln button, which is over on the right-hand side. We were using e to the x in the second menu last day, so we should know where it is. But then if I hit ln, the decimal approximation of the log of 4 is 1.386294361. We understand that it keeps going beyond that. There's no reason why it wouldn't, right? So if you had to work with this number, you should store it, right? So let's store this in 1, and then we'll be able to use it, right? Or if you want to do, because really what we have to find is the log of 4 divided by the log of 3. So whether you want to store it and then divide it by the log of 3, that's fine. Or you can just do it in one go. You're going to have to practice using your calculator. I know that sounds silly, but you're going to have to practice using your calculator because it doesn't work quite the same, right? It likes to have whatever it's putting in on the screen first, and then you tell it what to do with it, right? That's a little bit backwards from most calculators that I've worked with, at least. So we have to do 4 and the log of 4, and then sometimes I'll just hit equals just to make sure that it's actually done it, right? You don't have to, but, and then divided by, and I'm gonna throw some brackets around the log of 3 just to make sure, because I want it to treat it as its own thing. 3 ln end bracket equals, right? You have to hit that equals, otherwise it's just going to show you the log of 3, which you don't necessarily want. So we get 1.26185, blah, 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 blah. Okay. So to calculate the log of 4 divided by the log of 3, what you're going to do is you're going to have the 4 on the screen, and then hit the ln button, then hit the division button, and just to be careful, I'm going to throw brackets around here. I don't think you need them. We can check, but I don't think you need them, but just in case. 3 ln end bracket, and then the equals button. And we'll find that x is approximately equal to, right? I use that squiggly equal sign to say, hey, this is a decimal approximation. I understand it keeps going, but if I need a number to talk about, then this is what I would use. 1.261859507, only because I have it here. Okay, so make sure that that's what you get when you do this calculation on your calculator, whatever version you have. Oh yeah, so you can find log 4 and log 3, store each of those, and then do recall 1 over recall 2. That's totally fine. Oh, and thanks, Logan. It seems to work without the brackets as well. So I'll say that the brackets are optional. Right, and so good. That's just me being overly cautious, I guess, throwing those brackets on there, right? But just really make sure that you know how to do these calculations. Okay, good. So like I said, one of the reasons that we need to be able to solve for something that's in the exponent is because we have that formula on our formula sheet, and we need to be able to solve for all the things on our formula sheet, of course. So how about we do that as an example now, because we have everything that we need. Solve, and we don't know what the future value and the present value are. Well, maybe you do, but we as a class haven't talked about the future value and the present value quite yet. But of course we're getting there. But the future value and the present value, even though they're using 2 letters each, they're actually just one thing. So FV is one thing and PV is another thing, just so it doesn't get confusing. FV equals PV times 1 plus I to the power of n for n. Okay. If you kind of jump to your formula sheet, remember I told you the answer is on there already, but you still need to be able to show me how you got there, right? So one key thing is that having this multiplier out front isn't going to work when I take the log, right? I can only take the log of a base to the power of something and manipulate it that way. So I need to get this 1 plus I to the power of n on its own before I can take the log, right? So what I'm going to do is I'm going to divide both sides by PV, and then I'll be able to take the log, right? So I can only take the log of 1 plus I to the power of n if bringing down the n, which is what we want, right? So we need to isolate it. So we have, I'll write out the general equation again, FV equals PV times 1 plus I to the power of n. So first thing I'm going to do is I'm going to divide by PV. So I get the future value divided by the present value is going to be 1 plus I to the power of n. Now, what I'm going to do, because I want to bring this n downstairs, right, I need to take the log of both sides, right? And so here, this becomes the log of the future value over the present value. Should I do it right away? I'll just bring that n downstairs immediately, like I said before, right? Usually the only reason we take the log is to bring it downstairs. So it's okay to just jump right to that. So here is n times the log of 1 plus I, right? And this is by law number 1. Just in case you need to kind of convince yourself. You don't have to tell me what law you're using. I assume that you have them memorized, so you don't need to tell me. Okay, so if I'm trying to solve for n, well, now I just have n times something. So to solve for n, I just need to divide by both sides by the log of 1 plus I. So even though it looks a little bit bad, right, it's not actually, the math isn't that bad once we have logs. So I'm going to do the exact same thing that I did earlier. This becomes the log of the future value divided by the present value. Just kind of keeping it on one line like that over the log of 1 plus I. Which, if we go to our formula sheet, right, let's just have a look here, right? That is exactly what we have on our formula sheet. So like I said, you don't need to do that calculation every time, but I do need you to know how we got here, right? So that's how we got there with logs. Okay, let's do another example. This is example 128 from your textbook. Solve 3 plus y to the power of x is equal to 34. Notice that here we've got two variables, right? So I'm going to tell you which one to solve for. We're going to solve for x, but it also means that we don't know y. We're just going to keep it as a placeholder, right? So sometimes we're going to need to be able to work with multiple variables, but we're solving for one of these. So we're solving this for x. Right, and so I'll make a little note here. Notice y will be kept as a variable, but it's not the one we're solving for, right? So we can just kind of, it's no different than this 3, right? 3y, whatever, just placeholders. So let's just write out this equation again. 3 plus y to the power of x is equal to 34. So now, if I'm trying to solve for x, I know I have to use logs to bring this x downstairs, right? And I need to make sure that I've only got it as a power on one side. So I need to isolate it first before I can bring it downstairs. But it's already isolated. So now I can take the log of both sides. I'm going to do that quick maneuver, right? And just say x times the log of 3 plus y is equal to the log of 34. You don't want to forget to take the log of both sides, right? So this becomes x times the log of 3 plus y is the log of 34. We need to take the log of both sides. Solving for x, well, that just means I have to divide both sides by the log of 3 plus y. So I have the log of 34 over the log of 3 plus y. Now, it might be tempting, but we actually can't simplify this any further. How come? Well, one, we don't know why, so we don't know why. We don't know the variable y, so that's kind of a hiccup. But also, we only have laws for simplifying two logs being added or subtracted, right? So we actually don't have any shortcuts for simplifying two logs that are being divided or multiplied, right? So that's just something to keep in mind, right? We can't simplify this any further because we only have simplification rules for logs being added or subtracted. Okay, so let me write that down. Note, we can't simplify this any further because we only have rules for simplifying logs being added or subtracted. Being added or subtracted. Right? Not divided or multiplied. Multiplied. Okay, so that's just something to keep in mind because I know a lot of people want to smush these logs together, but it doesn't work like that. Okay. Good. Okay. So that's logs. Those are logs. Anyways, well, that's it for logs for now. Okay. But you do want to make sure that you know how to use your calculator to find these logs, but also kind of have a good handle on those log laws. Okay. I feel like there was something else. Oh, that's what it was. And you know what? I'm going to scroll to the top of our notes because I posted assignment 5, and assignment 5 is due next Thursday. And I might bump it till a little bit later, depending on how far we get today. But you'll be able to do most of it after today. Okay, so I'm going to scroll to the top of our notes just so it's there. Oh, I didn't leave myself a ton of room, did I? Assignment number 5 is due Thursday, the 4th, March 4th. Okay. And it's going to be on chapter 4 stuff up until a point. I haven't actually pinpointed up until what point, so I'll write on the assignment what sections, and then we can kind of see how far we get today. You will be able to do most of it after today. Okay. So like I said, sorry, it got a little, but I wanted it at the top of the notes. Should have remembered earlier. So we'll see how far we get today, and then, but you'll be able to do most of it after today. So the moment we've all been waiting for, especially me because I know what's coming. And it is so much more fun than the stuff that we have been doing. I think it's fun, but I know historically my students don't think it's that fun what we have been doing. So if you didn't like it, here's a different flavor. So section 4.2 is on simple interest. So here we go. At the beginning of each of these chapters now, or even the sections, we're going to have to establish a lot of terminology. So just like we did earlier, where we had to talk about, okay, what's S, what's C, what's P, what's E, right? What are all these things, so that when we read the problem, we're able to pick out the information that we're given, right? Same idea here. We're going to have to trudge through and kind of establish some definitions, but then once we have them, they're going to be ours to use. So first thing I want to do is I just want to bring in that section of our formula sheet that we're going to be talking about, right? And so the simple interest section on our formula sheet is this one here, and it's even called simple interest. Okay. So this is from our formula sheet. And we've got a couple of things that we need to have a good handle on, right? And so we've already kind of seen something like this. So the future value kind of shows up multiple times. P is in each of these formulas, right? So let's just kind of underline. So P is kind of our most popular little guy here, right? We said the future value, okay, that's here and that's here, without knowing anything about these formulas, right? So I'm just picking these things apart, seeing how many unique items are actually in here to work with, right? And so I is on its own. So I'll use kind of a neon green there. R, just plain old R, shows up in two of these equations. Now, notice that R1, R2, Rm, those are also rates, right? Spoiler alert, but those are going to be interest rates. And this is just going to be a special case of this formula here. More often than not, we're going to use this formula, right? But this one is just an extension of this previous one. What color haven't I used? Purple. Then we've got T shows up here, T shows up here, and also we've got some version of T1, T2, Tm. Okay. So here, notice actually I shouldn't, sorry, I didn't want to write it like that. There, I'll kind of highlight that that's the whole thing that I'm talking about. Notice this is just a different version, or kind of a more advanced version of this function here, or this, this formula here, let's call it, is just a more advanced version of the future values P times 1 plus R times T. Again, I know we haven't established what any of these things are, right? But I want to pick apart the formula sheet so that you can see that there's actually not a lot of stuff going on here. Okay. we're not going to get to this until the end of chapter 4, but this, and we don't use this formula a lot, but it's if the interest rate R changes over different time periods, T1, T2, Tm, right, allowing for M changes. Most of the time, we're just going to say, hey, I'm investing some principal amount, okay, so some amount, P is my initial amount, and it's at an interest rate of R for some amount of time T, right? My future value is always going to be, okay, well, how much money do I have in the end? What total amount, including P, so including my initial investment, will I have at the end, right? So these two formulas are doing the same thing. The only one that's a little bit different is this first one. We start here, and then what I find is that a lot of people just want to stay with this formula. If you want to ignore this formula, I would be happier if you did that and just kind of tune me out for the next 5 minutes, because most people just want to use this formula and it just won't work. You have to use this formula. But so like I said, kind of don't put too much emphasis on this formula, right? We'll start there, okay? But then once we get into using the future value formula, that's when I want you to tune back in. But it's on the formula sheet, so we should probably know what it is. So capital I, is the amount of interest that we've earned, okay? So this is going to be a dollar amount, okay? P, we already established, is the principal amount that I've invested. So P is the principal amount. And for some reason, for simple interest, we call it the principal amount. And then as soon as we move to compound interest, we call it PV, which is the present value, right? And so either way, just kind of use them interchangeably. So first thing I want to establish here is that where P is the principal investment amount, okay, and I'll just make a note here that later we call this PV for present value. But I don't want you to get confused later on when we start talking about PV. It's just for simple interest situations, we use P instead of PV for some reason. I don't know. Okay, so, okay. We all kind of, hopefully because you're in business, I am assuming that you all understand that you can take some amount of money, you can take it to the bank, and they offer you some interest rate. So you deposit your money, and of course they use your money, blah, 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 whatever, it doesn't matter. And in return, they give you some amount of interest. So you agree on some amount of interest, and you keep it there for some length of time. And then at the end, you'll have a sum that you'll be able to withdraw, right? And it's going to be larger than what you invested. And that's just investing, right? And so, or ideally, it's going to be larger than what you invested. Okay, so there's going to be two separate ideas here. You could talk about the amount of interest that you've earned, right? So the amount of interest is I, okay? And then the total sum at the end is going to be the future value, right? So think, okay, so after it's all done, after it's all sat there and invested and done its thing, then I have some future value, which actually includes the present value, right? Or the principal investment. So we need to establish what R is. So lowercase r is going to be the interest rate, the annual interest rate, but we have to use a decimal, okay? So even though we talk about, okay, I'll give you 2% interest, right? You would have to use 0.02 in your calculations, right? So this is our annual interest rate. As a decimal, right? So something like 2%, use 0.02 in your calculations. Often you can just assume that it's an annual interest rate unless it says otherwise, but usually these things are always annual interest rates. Okay. T, what's important about T is that T is the time in years, right? So if you're investing for 6 months, right, that's only half a year, right? And so then your T would be 0.5. So you always have to convert it to years, and we're going to spend a lot of time kind of talking about the rules for that. And also our fancy calculator has a days between dates calculator, so we'll be able to find the exact number of days between two dates, okay? Which we'll use to find T later on. So T is the time in years, okay, and that's going to be super, super important. Right, so if I tell you 6 months, T would be 0.5. Okay, so it has to be in years, otherwise it's not going to work. So let's talk about the future value first. The future value is going to be the total amount that you could withdraw at the end of this investment. So the future value, FV is the future value, is the total value of the investment at the end of the term. Okay. And by the end of the term, I mean at the end of the T, the time in years, right? So however long, okay, I'm going to invest this thing for 6 months. Okay, so at the end of 6 months then. Okay. And then the only other thing that's kind of new on here, right? We've kind of dodged this I keep talking about it, but then not actually saying anything about it. So I is the amount of interest, right? So that's going to be the same as the future value minus the principal investment, right? Whatever the difference is there is the amount of interest. Okay, so I is the amount, amount of interest earned. Right, at the end of the term or by the end of the term. Oops. And just so we're clear here, the amount of interest is going to be the future value minus the initial investment. So even if we didn't have a formula for I, we would most likely, depending on the information that we had, we would be able to find it just using that future value formula and knowing P. Okay. So, okay. Let's see here. What else is there? I think that's it. Okay. So you're, just to kind of set the stage here, you have some principal amount P. You take it to the bank. They offer you some rate, some annual rate R for some amount of time T, right, in years. Then you say, done deal, let's do it. You give them your money. It sits there for that term, right? That term, the investment term. And then when you come to take it out, you have a final future value, right? So you have a final dollar amount that you're able to withdraw. But also from there, you'll be able to calculate, okay, well, how much interest did I make here, right? And like I said, we're just going to ignore this little guy here, but it has the same structure, right? We're just going to be able to vary the rate, right? And so we'll look at some examples where, okay, so for the first 6 months, you get a rate of 1%. And then for the next 2 months, you get a rate of 2%. And then for the next 3 months, you get a rate of 6%. Wow, nice. Right, something like that. Different time periods, different rates, we'll be able to handle that. Okay. So a lot of definitions. What I do want to say about simple interest is that simple interest, you take your money to the bank, you put it in, and then at the end, they just give you some amount back. Okay. Whereas later on in compound interest, and we've already talked about this, but then that interest that you've made in some amount of time, so say you're compounding monthly, for example, at the end of each month, they add that little bit of interest that you made that month, and then you're making money off of that interest as well as your principal amount, right? So it's compounding at every month in that scenario. Simple interest is not that common for investments. I guess it's more for investments kind of less than a year, right? Then you might use simple interest. So kind of short-term investments would use simple interest, but it's not terribly common to have simple interest. Usually we're dealing with compound interest. So it's a good starting point, but more realistically, if you go to the bank, you'll be dealing with compound interest. So I'll just make a note of that here. So simple interest is usually only used for short-term investments. Or loans, right? Maybe loans. Okay, so, all right. The key is going to be, again, just like before, we need to be able to tease out information that we've been given and kind of pick a formula. Now we only really have 2 to choose from. And we plug it in, solve our values, and then we're done. So let's do, I'll bring in this example, and then I'll give you guys a little break before we actually go ahead and do this, but I wanted to have it on the screen so you can look at it and maybe try it out. Let's have a quick break until 11:10. That break was way too long. Hopefully you got everything done that you needed to get done. Water, coffee. Stay hydrated. Okay, so, all right, we're just gonna jump right into it. And first thing we're gonna do is we're gonna try to figure out, okay, what are we given here? What do we need to solve for, right? And so if $5,000 interest, okay, that looks like an interest amount to me, right? Is earned in 1 year, So, okay, so now I know how long it was invested for. At an interest rate of 7.3%, okay, so I have my interest rate, what amount was initially invested? All right, so I'm going to break this down, and I'm just going to highlight what each of these things are. Right, so here, that looks like the amount of interest to me, which we denote by a capital I. It was invested for 1 year, okay? Remember, T we use for time, and T is in years, and so T equals 1. And maybe what I'll do is I'll just kind of say I equals 5,000, T equals 1, okay? At an interest rate of 7.3%, but remember we have to use the decimal version. So unless you're super, super sure, I want you to make sure that you use your calculator. Just take 7.3 divided by 100, or I think even the percentage button. I can't remember which way it uses. Oh, Kia, weird. Okay. Anyways, right, see you've got this percentage button on the left-hand side. So I'm pretty sure, let me just play around with it here, 7.3, and then if I hit percent, it converts it to a decimal. How silly is that there's a button for it? But I mean, it's there, so you can use it, or you can do 7.3 divided by 100. Same thing, 0.073. So just make sure that you have enough zeros, because that can really mess some things up. So my R, right, is the interest rate, is going to be 0.073. And then it's asking what amount was initially invested. Well, the amount that was initially invested, right, we want to find P. Okay. So because I have my I, right, I am going to use the I equals PRT formula, right? I'm going to show you how you could use both. Well, maybe not this one because it makes it more complicated, right? But because I have the amount of interest, this is the only time that I'm going to use the I equals PRT formula. So since we are given I, we will use I equals PRT as our formula to solve for P. Right? I have I want to find P, I have R, and I have T. So I can just rearrange this thing and solve for P. Whether you do that with the variables or with numbers inside, it really doesn't matter. I'm going to plug in the values first and then solve for P. But like I said, it doesn't matter. So I equals PRT. So 5,000. It's a lot of interest to make. So I'm expecting P to be quite a large amount. Now 7.3% is quite high. So, but I'm still expecting P to be quite a large amount. And it's going to be good to develop those kind of checkpoints, right? Okay, does that P make sense? Okay, I'm moving on. So P times R, which is 0.073, times T, which is 1. Solving for P, what I have to do, well, 1 kind of flies away, right? 0.073 times 1 is just 0.073. So solving for P here, I need to divide both sides by 0.073. So doing my switcheroo, I get 5,000 divided by 0.073. On our calculator, do I have it here? 5,000 divided by 0.073, 68,493.1506 something. I can't see because my webcam. 68. It's right in front of me. I don't know why I did that. Got it in 2 spots. So P is a dollar amount, but what I want you to get in the habit of is just writing out the entire amount first and then rounding to 2 decimal places. And that's really just to make sure that you get the most marks possible, because if you round incorrectly, I'll take marks off. But if you show me the entire answer, I'll take fewer marks off if you round incorrectly. Right? So it's really just a safeguard for your marks that we're doing this. So hopefully I have, okay. It became 68,493.15, what was it? 15068. Okay. Remember, Moodle doesn't like the commas, right? We like them visually because it helps us see the magnitude of this number, right? But Moodle doesn't like them. P then as a dollar amount to 2 decimal places, 68,493.15, 15 pennies. Okay, so like I said, quite a large amount, 68,000 being invested at 7.3%. Good luck. If you find 7.3% anywhere, let me know. But that would give you $5,000 in interest at the end of the year. It's pretty good. Sign me up. Maybe as an assignment, I should get you guys to find out actual interest rates. They're a little bit depressing. So maybe I won't do that. Okay, so let's do another one. Let's do another example here. So from here on out, all these sections are going to start the same way, right? We establish some terminology. We establish just what are all these variables, what are all the things we could be talking about, and then we just use them in examples. And I just show you different examples which are meant to highlight different ways or different problems that you could come across, right? And so, but you do kind of have to think outside the box for some of these assignment questions, especially. Some of them are a little bit trickier, right? So you do have to kind of think outside the box a little bit, or think outside the bun. Is that Wendy's or can't remember? It doesn't matter. Okay, so example 137. Jim's calculations show that the total interest owed to Jill on his $2,700 loan is $315.90. If he paid simple interest at a rate of 0.9% per month, so here's where I need you to react a little bit, because for simple interest, the rate has to be per year, right? If you go back to our definition for R, I want you to think, okay, well, it has to be actually per year in my formula, right? So here, that's something I need you to react to. For how long did Jim borrow the money? Okay, so we're asked to find T, right? So again, let's go through and kind of figure out, tease out all the information that we're given. So it looks like here, the initial amount of the loan, okay, so loans and investments behave the same way. Whether you're depositing money, that's basically the bank is borrowing money from you and they're paying you interest, or you borrow money from the bank and you pay them interest, right? It's the same thing. So P is going to be $2,700. And then it says that the total interest owed is $315.90. So that's a dollar amount. So that means capital I is $315.90. Okay. So then if he paid simple interest at a rate of 0.9% per month, we need to do a little bit of work here and say that the R must be 0.9 times 12, right? Because there's 12 months, and we'll establish kind of the, but I assume that you know that there are 12 months in a year, right? 52 weeks, 365 days is what we'll use in this course in a year. So just kind of those guidelines. So we need to multiply it by 12 to get it per year, right? So it's actually 0.9% times 12. Okay. And so 0.9 times 12, I better just do it here, running the risk of having another add, 10.8%. Okay, but I need that as a decimal in my calculations, right? And so that's going to be 0.108. So R equals 10.8%, or R is 0.108 in our calculations. Right? Notice that you have to drop that percentage if you've already converted it to a decimal. And then we're asked to find T. Okay. Okay. Again, because I'm given the amount of the investment and I have P, I could go ahead and use that future value equals P times 1 plus R times T formula. But in this section, we are just using the I equals PRT formula. But I just want you to notice that the future value is just P plus I. So you could use that formula that I'm kind of pushing you towards, that we haven't started with yet, but I'm pushing you towards it. So, but for now, let's just use I equals PRT because, well, I have P, I have now found R, and I need to find T. It looks like a pretty good option to me. So I was $315.90 equals P, which was 2,700, times R, which is 0.108, times T, which we're trying to find. I'm actually going to do this on the side here because going back and forth, again, I run the risk of adds, and it's really annoying. 2,700 times 0.108. So what I'm going to do is I'm going to simplify this guy here first before I divide it over. You don't have to. You could divide each of these over here, but that just feels like a lot of work. So 315.90 is 291.6 times T. Right, multiplying those two out first. Then solving for T, I get 315.90 divided by 291.6. T, I get is roughly 1.083 repeating years. Now, I would just keep it as 0.083 years. I would just use the decimal approximation here. Usually that's going to be fine, right? We don't need to talk about years and months, right? How many months is 0.083? It's a little bit overkill. So let's just decide that t is going to be just decimal approximations, and most of the time that's going to be fine. If t ended up being something easy like 1.5, then you could say, okay, that's 1 year and 6 months, right? So if it's reasonable, then you can convert it into years and months, but most of the time I just use a decimal approximation. And here I just want you to note we could have used the fact, and this is just going back to what I was saying earlier, the fact that the future value is p plus I, and then used FV equals P times 1 plus R times T to solve for T instead. But we haven't really talked about that formula yet, but that's why, so this is the formula that I want you to focus on, right? Even though we're starting with this other one, but anyways, hopefully we're done with it soon. The reason I don't like it so much is because it confuses a lot of people. They want to use it all the time. Okay. Let's do another problem. Notice that we're going to work through these, and most of the time we end up solving for one of the things in the formula as we introduce a new formula. So just paid interest charges of 169.05. So the amount of interest is 169.05. So right away, I'm just going to make a note here, right? I know I is 169.05. On a $4,830 invoice, so the initial amount that she borrowed in this case, or owed, P is 48.30. That was 2 months overdue. So unfortunately for us, right, depositing money and letting it grow, it behaves the same way as, okay, so now your invoice is overdue and now you're paying interest, right? We know about all these concepts, right? We just don't maybe know the math around it. So she's got this invoice, it's 2 months overdue, and they said, hey, as soon as it's overdue, we start charging you interest. And then eventually we want to find what monthly rate of simple interest was she charged, right? And so for 2 months, so here we've got T is 2 months. What's important though is T has to be in years. So for months to go to years, we use T equals 2 divided by 12, right? 2 months in a year, or 12 months in a year, so 2 out of 12 months. And then we want to find R monthly right? So a couple of subtle things that we need to pay attention to. Yeah. So I have I have P, I have T, I want to find R. Again, the kind of the most obvious formula to use here is I equals PRT. So what I'm going to do is I'm going to solve for R, but remembering that R is per year, right? And then, so what I can do to get it to monthly is I can divide it by 12, and then that's my monthly interest rate. Right? So I equals 169.05. P was 48.30. R is what I'm trying to solve for, and T is going to be 2/12. Do not use a decimal approximation here. If you do, you have to store it in your calculator, right? So 2 divided by 12, oops, 2 divided by 12 is 0.1666 repeating. I don't want you to round that or anything. I want you to use the whole thing, right? So you have to use the whole 2/12. Okay. Trying to solve for R here, what I'm going to do is I'm going to simplify, because these are all multiplied together, I can just multiply across, right? And so 48.30 times 2 divided by 12 is how I would simplify this thing. And so I get 48.30 times 2 is 96.60 over 12. Times R is 169.05. So now, whether you want to use this in one kind of swoop, right? I actually break it up into 2 steps. I multiply the 12 over first, and then I divide by 96.60. Doesn't really matter which order you do it in. But we get 169.05 times 12 divided by, divided by 96.60 is R. Okay. So then 169.05 times 12 is, and again, you don't want to round anything. In this case, it comes up to a nice number, but it becomes 2028.6 over 96.60 is R. And here's where I decide to just switcheroo the sides. It doesn't matter. Divided by 96.60, I get an R of 0.21. Right. This is the annual rate. Okay. So the annual rate, well, it doesn't really look like annual. It's like annual. Well, so this is the annual rate, but we want monthly. So then R is going to be 0.21 divided by 12. So R is going to be 0.0175 monthly. But when we talk about rates, of course, usually we talk about percentages. And so this becomes, so R is 1.75% monthly. Oh yeah, so I like to break it down, but if you're comfortable just moving everything over in one go, that's totally fine. It just depends on where you are in your math career. But yeah, so someone asked if they could just do the math. Yeah, of course you can. But I like to break it down a little bit just so I'm not losing anyone here. So if you get to R equals 0.21 in the end, oops, lost you. You did it. Good, good, good. All right. So, like I said, in this next section, I'm going to show you how to use your calculator to find days between dates. So let's say, especially if we're talking about a really large interest rate, then people aren't going to be okay with rounding. Oh, 47 days. Oh, that's basically 2 months. No, not quite. Right. And so we're going to need to do math on 47 days, for example. Right. And so, especially if you're paying the interest, then you want to make sure that you're not overpaying. So, in section 4.3, we're using our calculator to find days between dates. Days between dates. And I am assuming that you have some sort of, like I said, I have this free app that I downloaded. I'm assuming you can do the same. So I am assuming that you have access to these. These days between dates calculators are all online too, so you should be able to find something. But we do need to use them. So using our calculator to find days between dates, which we usually abbreviate DBD, days between dates. Okay. So on your calculator, there's a date. Is it dates or date? A date function. It's in the second menu above the 1. So here, if you hit 1, right, I'm just kind of holding it down. There's the date menu. Okay, so you have to go second date. Okay, so let's do that. Second date. And let's just scroll through here and see what's going on first. So of course, if you need to find the days between dates, you need to have date 1, which is going to be kind of the, I'm thinking timeline wise, the leftmost date. So it has to go from date 1 to date 2. But then if you use the arrows, so see up at the top, you've got arrows, up and down arrows. I think we've already used them when we had to set up our calculator, right? So if you use the down arrow, you've got date 2. Okay, so we'll be able to change these dates. And then if you scroll down again, it'll tell you the number of days between those dates. Okay? And then if you scroll, I don't know what ACT is, but you can just ignore that. And you can just scroll through, right? Date 1, date 2, and then days between dates. Okay? We do need to know how to enter these things into our calculator. Okay? Our calculator will be able to find, if we give it 2 of the pieces of information, right? Whether it's the start date and the number of days, it'll be able to compute the date 2, right? What is that date? Or if we give it 2 dates, it'll be able to find the days between the dates. If we give it an end date and the days between the dates, it'll be able to find the start date, right? So of course, given any 2 pieces of information, it can find the third. Okay. So in the second menu, we find the date option above the number 1 button. Okay. So we enter that the date menu, we'll call it. And in the date menu, we have 3 different inputs. So in the date menu, we find 3 different inputs. First one is called date 1, okay, DT1. And this is going to be the start date. Then, of course, we have DT2, which is the end date. And then we have DBD, days between start and end dates. Okay, and here, scroll between these using, or I guess, sorry, I'll just check the order of those. It's down and then up. Now life insurance, okay. Oh, up and then down, okay, good. Nope, I had them backwards. Not that it matters. But at the top. Okay. So you can scroll between these and, right, and like we said, given any 2 of these, it'll be able to compute the third. Okay. So given 2 of date 1, date 2, and DBD, right, depending on the situation that we want to find here, and DBD, it will be able to compute and I'll just emphasize that compute is that CPT button in the top left-hand corner, the third. Okay. What we need to learn is we need to know how to enter dates into date 1 and date 2, right? So it's going to require a specific format, and that format is month, month, dot, day, day, year, year. Okay. To enter dates, we need to use the format, and it might be useful to kind of have this, add this to your formula sheet or add it to your cheat sheet or whatever you have going on, because we're going to use the days between dates calculation quite a bit. So you'll need to know how to enter these dates, however you choose to memorize that. So to enter dates, we need to use the format month, month, dot, day, day, year, year. I will say that it was extremely short-sighted of them to only have 2 values for the year, year. So we'll see how this app works. But in the handheld calculator, there's a year where it switches over. And I think it used to be 18 where it switched to, so from 1918 to 2018, right? 18, it's not very helpful. So you might come across something like that. I'll try to avoid it, but if we stick to kind of years close to here, then we're fine. But it extremely short-sighted. I don't know why they would do that, but only use 2 values for the year. So dumb. Anyways, so we need to use this format, right? So that means that when I give you a date, you'll need to convert it to this format. And then in order for it to lock in, you need to hit enter, okay? And in order to lock in the date, you need to hit enter. Right? So it needs to kind of store it, okay, by hitting enter. So let's see here. Do I have, all right. Let's do an example where we have to find the days between the dates. So calculate the amount of interest owed. So I, right, is the amount of interest. And I'll do that thing again, and the amount of interest is I on a loan of 3,800. So P is 3,800, which was advanced on June 17th, 2005, and repaid on October 1st, 2005, at a rate of interest of 10.75%. So I will say this, that R is 0.1075, converting it to a decimal right away. Okay, so June 17th comes before October 1st. So here, date one is going to be June 17th. And usually I just write it in this format right away, month, month, day, day, year, year. But maybe I shouldn't cram it in there. I'll just say that's date one and this is date two. To show my work for these days between dates calculations, I always write it out like this, and I want you to do the same. Date one, date two, and then the days between dates. First thing I'm going to do is I'm just going to write out the actual dates, right? June 17th, 2005, June 17th, 2005. And then up above here, I'm just going to make a note to myself that I need to convert that to month, month, dot, day, day, year, year. Okay. And then I have October 1st, 2005, which I also need to convert to month, month, dot, day, day, year, year. And what I do is I use a little star to indicate which one I'm solving for, right? And so here, use an asterisk to indicate which of the three you are solving for. And that's something that we're going to use throughout the course, because a lot of this work is going to be calculator work. And so the calculator is going to do most of the calculations, but we need to kind of walk our reader through what we're doing here. And so when I put a little star here, that says, okay, and then I use my calculator to find that. And I know I'm out of time here, but June is the 6th month, right? So 06.1705, right? If you had to convert it to month, month, day, day, year, year. October, September, October, I always have to have a jumping off point. October is the 10th month. And the first day of the 05 year. Okay, so just, I know quickly, because we've got more examples of this for next day, but quickly, let's just do this in our calculator. So I'm already in the date menu, and I said 06.1705. Notice that it hasn't stored it, so you have to hit enter. When it's stored, it'll show it like that. Then you can step down and say 10.0105. Again, you have to hit enter. And I'm rushing through this because I want the answer on here. Now I step down and I can compute using that CPT button in the top left-hand corner, compute the days between dates, 106. Yeah. So I'm just gonna jot that down, but of course we're gonna come back to this next day. So 106. Nice. Okay, I know I'm out of time. Sorry for keeping you. If you have any questions, let me know. Otherwise, have a great weekend. I'll see you again on Tuesday.
Thank you, Emily.
Thank you.